Today we're starting with the endocrine system, and we will also cover Chapter 21, Blood, in preparation for Exam 1. The endocrine system is a very diverse system. There are a lot of dedicated glands, and there are also a lot of organs that also can secrete hormones, and we can treat them as endocrine organs as well. So we're going to start, it's kind of going to be a top-down, superior to inferior approach. We'll cover exactly what we mean by endocrine signaling in general, what hormones actually are. Then we're going to go from the hypothalamus to the pituitary to the thyroid and parathyroid, then move down to the adrenal and pancreas. Then we're going to zoom back up to the pineal and thymus just to clean up there at the end. And then we'll cover some other organs that have different functions that can also function as endocrine organs. The kidneys, the heart, the GI tract, the gonads all have other functions, primary functions and secondary functions as endocrine organs. So this is what your endocrine system looks like. You'll notice it's got a lot of other organs that you probably already know a little bit about. And as I said, we're just going to do a top-down approach. So endocrine glands are ductless. So this is going to differentiate it from exocrine glands, which you may have heard of. Exocrine glands secrete cellular products into ducts. Endocrine organs secrete hormones into the bloodstream. They just act via simple diffusion for the most part. So since endocrine organs rely on secreting into the bloodstream, they will all have extensive blood vessels in them. This is a great crossover between the nervous system and the rest of the body that we're going to cover for the rest of the semester, because this is a sort of intermediate between the nervous system and everything else. So obviously you have innervation to everything. You have autonomic innervation to all of your smooth muscle of your GI. You have, sympathetic and parasympathetic innervation to all of these different organs. You also have hormonal control. It's just at a slightly different level, a slightly different pace, and a slightly different context and sometimes function for endocrine signaling. So we can also differentiate the nervous system from the endocrine system. With the nervous system, we're going to have a neuron. Let me get my pointer up here. I always forget it. You can't see my pointer until I go like this. Okay. You've got a neuron here, and that is going to secrete a neurotransmitter directly onto the target cells, and those target cells will have a receptor for that neurotransmitter specifically. If there was no receptor for that neurotransmitter, this neuron would not be secreting to these cells. It would die off. If it didn't work, it wouldn't be there. By contrast, endocrine glands secrete their hormones into the bloodstream, and those will circulate around the entire body. There will be cells that they reach here and here and here, but the cells they affect, and this is very key here, the cells they affect have receptors for that hormone. So they're reaching everywhere. They're not going to be very specific in where they go, but the cells that respond to them will have receptors for that hormone. So some hormones are going to act very specifically. Let's say the target is fat. The only cells that will have a receptor for that hormone will be adipose cells. Even though that hormone's going everywhere, only the adipose will respond to it. But then let's take something like thyroid hormone that's going to control how all of your cells metabolize. Pretty much every cell is going to have a receptor for thyroid hormone, all of them. So there's going to be a lot of specificity, and there's going to be a lot of form and function, where some things will have very, very specific targets, and only a handful of cells and cell types will have receptors, and others will have very broad functions and have many, many cells with receptors for that hormone. Yes?
So does that mean that for every, so for the adipose and thyroid and everything, that's going everywhere?
It is going everywhere, yes.
Just those places can accept it?
Yep.
So
It has to act via diffusion. It's just going where it's going, and it's going to circulate everywhere that the bloodstream goes. But the only ones that will respond to it are the ones with the receptors. So yes, that was accurate. Yes?
Are there cells with multiple different kinds of receptors?
Absolutely. Many cells will have different receptors for growth hormone, thyroid hormone, and then any other hormone it responds to. Yes, cells have multiple types of receptors on them. Absolutely. So here's an example of that selectivity of hormones. Hormone A will have a receptor for hormone A. If hormone B arrives at that cell, it will not respond to hormone B because it does not have the receptor for it. Here's a cell that has a receptor for both hormone A and hormone B, and here's a cell that has only receptors for hormone B. So that's exactly what we were just saying. Yes?
So what happens to the cell of the hormone B? It just floats around until it finds...
Yeah, so hormone B on this, if it goes near this cell, it'll just keep diffusing until either it's broken down, wastes away, or until it finds a cell that has a receptor for it. That is correct.
Is there a time limit on that?
There is a time limit, so it's not something we go into a considerable amount of detail about today, but there are half-lives for both hormones and drugs. That's a kind of a farm concept. So there's a certain amount of time that hormones survive in your system before being broken down by your liver, for example, is one option. And it's slightly different for different hormones. So something like epinephrine, norepinephrine, I think, is a little bit faster than some other hormones, but don't quote me on that. Of course, it's on YouTube now, but whatever. I've never memorized any half-lives of any hormones, is what that means. Okay, hormones. So endocrine system is the hormone system. Endocrine signaling is in that sort of naming convention with paracrine, autocrine signaling. It's just cell-to-cell signaling types, with endocrine just meaning it's going systemically through the bloodstream. Okay, you have some classes of hormones that we probably won't focus on too much. Peptide hormones, steroid hormones, biogenic amines. Most of the ones we're going to focus on are peptide hormones. Sex steroid hormones, so testosterone and estrogen are steroids. There is some clinical application to this knowledge. For example, steroids are generally smaller and nonpolar, which means what for the plasma membrane? Yeah, it can go through. It can simply diffuse through a plasma membrane. So things like estrogen don't really need a specific receptor. They can just go into your cells and wreak some havoc, which is exactly what they do. So that's the clinical significance of these hormone chemical structures and classes. Most of the ones we're going to work with are going to be peptides, so protein-based. We're going to focus on most of those. We do need to review positive and negative feedback systems, and this should be very closely tied into your concept of homeostasis. So in homeostasis, you have a sensor that detects a state. You have a control center that integrates that information, and you have an effector. I'm worried that my mic's not working. It's not giving me signals for this.